Welcome to an in-depth overview of H3MP. This video will be mainly for modders who will want to add support for H3MP to their mods, or people who want to contribute to H3MP. So I'll start by going over the general structure of the mod, then I'll explain the way the networking is set up. I'll go through and explain the tracked types and the entire TrackedObject system. And then I'll be explaining how customization and mod support and compatibility can be added using custom packets and the TrackedObject system. And finally, I'll be hoping to show an example of how I add support for custom types and to show the entire process practically. So starting with the general structure of the mod, I might be going line by line for a little bit just to show how H3MP is initialized. So the class mod is the entry point to the mod. It is the BepInEx plugin. Everything starts in the start method, where I go and initialize everything. In the init here, H3MP will start by finding itself its own path. This is where it will be looking for the config file and the assets file, and any other file that it might need. It'll start by getting the tracked object types. This, I'll come back to it later as well, as it will be relevant to the customization and mod compatibility. Essentially, you can have your own track types supported by H3MP, and this is where H3MP will go and find them using reflection. So again, I'll just come back through this later and show more in depth how it works once we go over mod compatibility process. Once we're done getting the track types, I start with doing all the patches that H3MP is going to need. So I have a patch controller class, which controls all the patches. All of my patches are in their own classes as well. Each class corresponds to a certain type of patch. So I have general patches, any patch that is relevant to the mod itself. Interaction patches, any patch that has to do with the player's interaction with certain objects. Action patches, any action. So, for example, how I know when someone fires a weapon is through one of those patches. Instantiation patches is anything that has to do with object instantiation. So anytime an object is instantiated, I keep track of that because H3MP has to possibly start tracking the object to sync it over the network. Damage patches is anything that is relevant to damageable interface. And TNH patches, anything that is relevant to TNH. In the patching, I start with getting compatibility data. This is specifically for me. It's just mods that H3MP supports explicitly. Currently, this is only TNH Tweaker. So this is where I get all of the methods and fields that I'm going to need later to support it. So you don't really have to care for this. It's not really important to you. Now when H3MP does its patches, it will always call a verify method that I wrote, which will be used to check the integrity of the patches. So some of you might have seen that H3MP comes with a patch hashes.json file. This file contains the hashes of every method that I patch. These hashes are then compared with the original method's code to verify if the method has been modified since the last time the patch hashes file was written. This isn't super useful to the users, it's really more for me. Again, it's just to know if the game has updated something that I patched so that I can adapt my patches to it. So this just helps me debug, and it'll let me know if my patches are broken. Each patch is done manually, so I just get the original method and then prefix, postfix, transpiler, and I patch it directly. In each of these classes, I have the do patching method, which will do all these manual patches, and then lower you'll see all the actual patches. So if you need to find anything specific to know how my patches are done, how they work, this is where you'll go and look for them. All these patches are within the patches folder of the project. So going back to mod, H3MP will then load its config. This is config.json file. It loads it as a JSON object, and this is how I'm going to read the your IP and username and such. This I will be modifying later on to put everything in game so that you don't have to actually edit the config.json file. And then H3MP will load its assets. These assets are a menu specific to TNH. It will load the player model. It will then load the Sausig wearable map, which I'll explain. It'll also load the TNH start equipment button. The Sausig wearable map, Sausig wearables, which refers to any of their clothing, any of their armor and helmets and such. The entity itself doesn't have an ID to identify it with. So when I go and track Sausigs and I go through the wearables have an ID, but it's not written anywhere on the entity itself, so I cannot identify the actual piece of clothing they have currently equipped, or at least not through some unique ID. So instead I use their name and then map it to their actual ID in the prefab dictionary of the game, and with that I can then identify it across the network. You don't need to pay any mind to this right now. I'll go back through it when I explain how tracked Sausig works. Once the assets are loaded, we subscribe to a couple of scene loading events. This is how H3MP will keep track of which scene each client is in. And this is essentially how H3MP sets itself up. Once this is done, H3MP will only ever do something again when either you start hosting or you connect to an existing server. Whether you host or connect, this will always create a manager object. The manager object is literally just an empty game object that is put into don't destroy on load, so that it stays alive whenever you change scene and all that. And attached to this object will be a thread manager and the actual game manager. The thread manager is what will manage anything that has to do with updates of the network, and when we update certain things such as player states and tracked objects and such. So the idea is that on every fixed update, if we're the host, we'll be going through every other player's player state and sending an update to every other client. This player update includes the player's ID, position, rotation of all the different parts, so like the hands and torso and head. It also includes their health and any other additional data that I might want to put in there as a byte array. Going back to thread manager, we then send an update of all the tracked objects. Again, I'll come back to this later when I give an overview of the tracked object system. And then finally, we send an update of our own player state to everybody else. The thread manager on every update will process the current queue of packets that it's received. When a packet is received, it will be put into a list called execute on main thread, which can essentially fill up between every update. And then every update, we're just going to copy that over to a different list, clear the current list, and then we're going to go and execute everything. I'll go over this in a bit more detail when I go over the networking setup. Then in the update, if we're not the host, if we're a client and we're trying to connect to a server, every second we're going to be sending a ping to the server, and if we're not yet connected, if we're still waiting for the connection, the client connection will time out after 30 attempts at sending a ping. It'll otherwise just send a ping, and with this it'll keep the TCP connection alive, because the TCP connection tends to time out after a little bit if nothing happens on it. This is essentially it for the thread manager. Now for the game manager, so we also add this to the manager object. The game manager is anything relevant to the multiplayer game that is currently ongoing. So this is where I'll keep all the player data, all the tracking data for all the different types that I have. It's where we'll be keeping track of all the instances and all the players and objects that I keep sorted by instance and scene. And this is where also I'll be keeping track of all the settings as well, so like the radar mode, radar color, nameplate mode, the color of the player, and all that. H3MP has an instance system. Again, I'll be going through this when I go over the network setup. So once the game manager is created and the connection is made, let's head back to where the connection is actually made here. H3MP will start keeping track of everything that happens. By this I mean through patches or changing scenes and such. For example, the patches. So let's check just a simple patch. This is the patch for whenever we interact with an interactive object. A patch will not happen if we don't have the manager object. So if we don't have the manager object, my patches get skipped. I never do anything. So H3MP doesn't do anything until a connection is made. Once there is a connection, H3MP will keep track of a bunch of events. In this case, we keep track of the current interactable of the Vive hands. This is mainly to keep track of if we are interacting with a tracked object we need to know, because some types of tracked objects might behave in certain ways depending on how they're being interacted with. So this is just a quick general example of it. One of the most important things that H3MP keeps track of is which scene a player or a client is currently in. Only a certain set of scenes are synced, so only in those scenes will we actually track everything. So we keep a list of all the scenes that should not be synchronized over in Game Manager. This comes in the form of a dictionary. This dictionary can be used by other mods. If they don't want a specific scene to be synchronized, they can add their scene in here. The string corresponds to the name of the scene, and the integer corresponds to the client ID that added the scene. So when we load into a new scene, we're only going to be tracking all the objects in that scene and synchronizing players if this scene is not in the non-synchronized scene dictionary. So how H3MP keeps track of which scene we're in, as indicated earlier, we subscribe to scene loading events. The main one here will be Game Manager's on scene loaded VR. And here, like the patches, if we're not connected, we don't do much. We just keep track of the scenes because I'm going to need it once the connection is done. So before we even connected, I keep track of a few things. Once we are connected though, I keep track of when we start loading and when we finish loading. So first I set a flag that I can access from anywhere saying that we are currently loading. There's some things that I don't want to have H3MP do while it's currently loading. This is how I'll know. I keep track of which instance and scene we are in when we start loading, and whether we're even connected at all. I'll come back to this also when we talk about tracked objects, but while we're loading, all objects in a scene will get destroyed. H3MP keeps tracks of object destruction, so that if an object is destroyed on one side, it can be destroyed on other client's side. But if a client leaves a scene with other players still in it, obviously we don't want it to just destroy all the items in the scene on all sides, so instead of destroying them, we're going to give control of the objects over to other clients that are still in the scene. So we'll see that entire process later. Once we enter a new scene, new objects will then be instantiated. I don't want to track these right away. I'm going to track them when I arrive in the scene. So here I want to just skip all instantiates while we're loading. So I increment this marker here just so I know not to track any instantiation using the instantiation patches. I then need to keep track of which players are currently there when we start loading, mostly just for giving the control, just so that I know which other players were there, so I know who to give control to. Then, if we arrive specifically in main menu, I need to deal with some TNH stuff. This is where I do it. This whole process assumes, though, that to go in any other scene or to switch game mode, a player must go through main menu. So you can't just transfer from a TNH map to another TNH map. You have to go from the TNH map over to the main menu and then to another TNH map. So if we go into the main menu, I know for a fact that we are not in TNH anymore. So this is how I clear everything I store, everything I track about TNH. I'll probably show in more detail how I deal with TNH specifically later on so that I can show this entire process. Then I check the players in the destination. This is specifically so that I know when I arrive at the scene, if there is already someone else, I don't want to track any object. This is because if someone is already in a scene, they already instantiated all the items that come with the scene. So then if you arrive in the same scene and you instantiate those items as well and you track them as well, then every client is told by H3MP to instantiate a double of that item in that scene. That ends up creating multiple of the same items. Clearly, we don't want that. So this is one way that I prevent it. There's multiple layers to this, obviously, because of synchronization. We might not necessarily know whether there is other people in the other scene yet. If, let's say, two players are loading into the same scene at the same time, obviously when they start loading and they both think that they're going to be first in the scene, then they're both going to instantiate. They're all going to track all the objects instantiated into the scene. So I have another layer later on that checks this again, and then even another prevention system after that. That essentially lets the server control who gets to initialize a scene. So we'll see that again later as well. I only track objects if they've been awoken. So if their awake method has been called, this is because something like the onDestroy method, which I'm dependent on to know if a tracked object has been destroyed, will not be called unless the object has been awoken. Anyway, if an object has not been awoken yet, it just means that it was never made active to begin with. So I just wait until they've awakened to actually track them. So if we leave a scene with items that have not been awoken, their destruction will not be tracked alongside the usual awoken items. So I have to go through all of the objects that we are tracking and make sure that we stop tracking them. So I remove them from any kind of local tracking list as soon as we start loading into a new scene. Then when we finish loading, I set the new scene that we're currently in. I set the flag of loading to false, and I send our new scene over to all the other clients so they know which scene we're in, so they can keep track of us. Here we check if we were connected when we started loading. This is important to keep track of whether we connected while we were loading. We don't want to decrement these if we were not connected at load start because we never incremented them in the first place. Then, once we arrive in the scene, I'll be checking if this scene is a scene that we want to synchronize. If this is a scene that we want to synchronize, we're going to be checking which other player is currently in the scene to again check if we should be in control of the item. So if we should track all the objects or let the other players though who are already in the scene track them. Then there is an important problem that comes with the way I track objects and the way I send updates over to all the different clients. To lighten the load on the network, I've made it so that a client doesn't send updates for an object if there are no other clients in the same scene as them. This means that when you're in a scene and you tracked your items, but you never sent an update out for those tracked objects, but then someone else comes into your scene, they need to know which tracked objects you have so that they can then instantiate them on their own side. To do this, obviously the server will have to send them all the data they're going to need, but the server never received the most up-to-date version of those tracked objects because no one else was in the scene, so no updates were ever sent. So I have an entire system for the server to request up-to-date object data when another client joins a scene with other people already in it, so that then the joining clients can then be sent the most up-to-date data that the server just got back from the clients that were already in the scene. Now in this case, when we finish loading, if we are the host, so if we are the server, and we join a scene, we just make sure that we have the most up-to-date objects from the clients that are already in that scene. So we will be adding ourselves to a list of clients that are waiting for an up-to-date object packet from this specific player that is already in the scene. And then I'll be adding that player to a list of players we are waiting for an update from. This way, when we receive the items, we can keep track of which ones we're actually waiting on, and if we are waiting for any more after that. And then I'll go ahead and make the request for these updated objects. Then for each player in the new scene, I also update whether they should be visible or not. So visibility can be set depending on multiple things. So whether the scene they are in should be synchronized, whether it is the same scene as ours, whether they are in the same instance as us, whether they are spectator hosts, which I might explain later, and whether their health is above 0, because obviously if they're dead you don't want to see them. And I do something specific for TNH as well. So I then set whether the player is visible or not. I'll later be adding a way for mods to override this, so they can also put their own kind of criteria to decide whether a player should be visible or not. Getting back to when we finish loading, so we update whether we want to track objects or not, depending on which player is already there, and then we go and track all the objects in the scene. I'll be going over this when I go over the tracked objects. Then, if we were given control of an object while we were loading into the scene somehow, we need to make sure that we instantiate this item once we arrive in the scene. This is where I do this. So any item that has not been instantiated yet and is not in the process of being instantiated already, I instantiate. I only do all this if obviously the scene must be synced. Otherwise, I update the player visibility and all of them will be set to invisible and nothing will be tracked. Then I update just the max health depending on the settings. So if you arrive in the scene, you need to check if that scene has a specific max health set by the host. This is why I do that. So I just check if there is already an entry for maximum health in this scene, an instance, and if there is, I set it accordingly. I often mentioned instances, so scene and instance. I guess we can start talking about the network setup, because this kind of turns more into the network. So I'll explain instances quickly. So a specific client can only be in one instance at a time. So an instance is really just an index, it's really just a number. By default, every client is in instance 0. I made instances specifically for TNH at first, because let's there are 4 people in a server, 2 of them want to play a game of TNH in a specific map with specific settings, and then the 2 other players want to play in the same map but with different settings. Even if they are in the same scene, they will not be synchronized and they'll be able to play independently because they will be in separate instances. So here I just keep track of how many players are in each instance through the active instances dictionary, and then I keep track of specifically the TNH instances, which has a bit more data, which I guess I can explain later when I go over TNH. But that's it. The instances are just a way to separate people, although they're in the same scene. Right now, you can't just set your instance. The instances are really just used in TNH for now, but this is useful for other mods who might want to do the same thing I did with TNH. So when I refer to scene instance, I specifically mean a combination of a scene and instance, so 2 players will only synchronize when they are in the same scene instance. The way I track players in their scene instance is through this dictionary right here. So every player is in here. I just keep the ID of the clients in the instance and in the scene. I do the same thing for objects, just so I know which objects to send to who when they join a scene, when they join an instance, and so on. So now I can start talking about the network, how that is set up, and then we can look at more events like the changing scene and all that are relevant. So the main 2 classes for the networking are server and client. Both of these have their own TCP and UDP classes, which are used to manage the sending and receiving of TCP and UDP packets respectively. The whole setup uses .NET's networking libraries, so .NET TCP clients and UDP clients as the sockets. So when I start hosting, for example, I'm going to call a start on the server with the maximum number of players who want on the server and the port, which are both taken from the config file. We then initialize the server data. This is initializing the client files, which I'll come back and explain, and all of our packet handlers So these are all the methods that will be handling certain types of packets. And then just initialize the lists and arrays that I have that are relevant to the server. Once this is initialized, I initialize the TCP and UDP listeners. The TCP listener will start accepting client connections, and UDP will simply start accepting UDP packets. When we connect, then I also sync all the tracked objects in our current scene. So this specifically to the server. I know there's no other players already in the same scene instance because we're the server. So when I start, I just track everything and I take control of everything. The TCP and UDP listeners each have their own callbacks. So let's say we receive a connection from a client. This callback will be called, we're going to get the data from the client, and then we're going to start accepting another TCP client connection. We're then going to use the client data to initialize everything about this client. So like I showed, when we initialize the server data, we initialize an array of clients. These clients are server clients, so these are just a class that exists to keep all the data about a remote client. So when a connection is received, we're going to go and get the socket of this client that we initialized earlier, and we're going to connect it using this TCP client data. The server client will then initialize itself and begin listening to any TCP packet we receive from this client. The server will then send a welcome packet over to the client, giving the client its ID and all the data that the client will need to initialize itself and its settings. So let's say the host already has set a nameplate mode, color by FF, radar mode, all that, and the maximum health in some scenes. This will all be sent to the client so that they can then send themselves accordingly. So we can go and check how the sending and receiving of packets happens. First though, note that a TCP connection must have this hold handshake happen so that we can set up the connection, while UDP will just set the endpoint of our client when we receive our first UDP packet from them. So continuing with the TCP connection process, the server will send a welcome packet over to the client when it connects. Like I showed earlier, this will contain all the data that the client will need to initialize itself. So this will create a packet with the packet ID welcome, which is just an entry in a hard-coded enum inside the packet class. We're going to look at it later. The server then sends the packet using a sender method send TCP data, specifies to which client, and it will use the server client's TCP instance to send the data over. So this will write the packet data to the stream for that client. When a client receives a packet, it will have to handle this packet. All the packet handlers are in client handle. So when a client receives a packet, this will be through the client TCP connect callback method. So this is just for the connection specifically. So upon connection, a client will be waiting for the connection packet, so in this case the welcome packet from the server, and once it receives this, it's going to call the connect callback method. It's going to get the data from the stream and it's going to make a new packet out of it. All this will be sent over to the receive callback, which is what will be used from then on to start receiving TCP data. So when a client receives a TCP packet, it's going to finish reading from the stream. If the length of the data is 0, it means that it's reached the end of the stream. This means that there is a disconnection that's happened. So in this case, we disconnect right away. If we have data to process, we copy all the data over to a data array from the received buffer. Now, a packet may not be sent in a single piece. If it's too large, it may be divided into multiple, so we have to take that into consideration. So we have to handle the case in which we don't have all the data from the packet right away. So when we send the data we've received over to handle data, this is where we'll decide whether we need to keep listening for more or whether we can actually process the packet. So when we receive data, we're going to be just writing it to our own packet. So then when we receive a packet, the first thing that will be written to a packet will be its length. So we read the length of the packet, and if the length is smaller or equal to 0, obviously there's nothing to process, so we're just going to return true. Returning true will make the received data reset itself. So now we can then read the next packet into it. Another thing in networking with TCP packets is that they can be merged. So multiple packets may be merged into the data that we received here. So in this case, we're going to keep checking if we have more packets to read. As long as we do, we're going to be adding this packet over to the list of packets to be processed by the thread manager that we saw earlier. So execute on main thread will add an action to the list. This will be the action that I'll be adding to the list. This is what thread manager will run when it processes all the packets. So in this action, we're going to rebuild the packet from the data that we got for that specific part of the data. So from this, we'll be getting a single packet. This packet will have a specific ID. So first we read the ID, and then we'll handle different cases depending on the ID. So a client's ID will be set to -1 by default until it receives the welcome packet, at which point it will receive the ID that it should set itself to. So if its ID is still lower than 0, it will only process the welcome packet. Otherwise, it should just ignore the packet because it just means that it was sent some data by the server, but it wasn't supposed to process it. So when we receive a packet, if the packet ID is lower than 0, this is a custom packet. This is specific to the customization and mod compatibility process that I set up. So we'll come back to this entire thing later. What is important now is when the packet ID is greater than 0. So it's a packet ID that can be found in one of these enums, essentially, and these will correspond to a packet handler in the array of packet handlers. So this list will be built between frames, and then the thread manager will be processing these on each update. So when we add an action to the list, we're just going to add it instead of flag saying that we have some actions to execute. Then when we actually do the update, if we have actions to execute, we're going to copy these over to another list of actions. We'll clear the main list, and then we will execute everything. What will be executed is exactly what happens here. So that is when we're going to be calling the packet handler corresponding to this packet. These packet handlers are all methods inside of server handle or client handle. In this case, we're receiving the welcome from the server, so we're going to be looking at client handle. This is the welcome packet handler. So this takes in the packet and then reads all the data from it. So this is all the data that we were in when we sent it from the server. So all the settings, the ID of the client, the welcome message. So we want to read the data exactly in the same order that it was written. So here we're just going to read the message, the ID, all the settings, and then we're going to initialize ourselves depending on all that data. The server will also send the custom packets that have already been registered. I'll come back to that later again. So when we join as a client, when we join a server, we also want to set our maximum health depending on that setting. So once it receives all that data, the client will also set its ID. I also set this in Game Manager ID just for convenience, so I'll always have to access the singleton of client. The client will then send a message to the server saying that it received the welcome. So it tells the server that the handshake was successfully completed, and then it will connect its UDP client to the server so that it can start sending and receiving UDP data to and from the server. The welcome received gives the server the details about this specific client. So this is where we'll be sending the server our username, the current scene instance we're in, our IFF, and some other settings that we have set. So like the client, this will go through the entire packet building process and will then be handled in server handle by the packet handler welcome received. So the server will then read all the data about the client and will send this client into the game. This just means that it makes a new player for this client. So we're going to send to every other client an order to spawn that client's player on their own side. We're going to spawn that client's player on our side. We're going to then send every other client's player over to this client, and then we'll tell the client to spawn the host's player. The server will then send all the up-to-date objects of that scene over to this client. So again, this comes back to the whole up-to-date object process that I showed before when we finish loading into a scene. The server will request up-to-date objects from every other client in the same scene instance as the new client, and only once it's received all of them will it send all the tracked objects over to that client. The client will then be able to instantiate those objects on their side if they're in the same scene instance as them. Once it's done doing that, the server will tell that client to sync all of its tracked objects. Upon the connection, also, the client will need to know which TNH instances already exist, so the server will send those as well. And this was also for mod compatibility, so this would let mods send whatever data they want over to a new client, but I'm gonna have to change this, so I'll make a note of it and I'll make it more accessible. So this is essentially the entire packet exchange that happens between a client and a server. Now, if we just go back quickly over to when we process the packet data we receive. So for each packet that we process in the possibly merged packets, we're going to check if there is more data to read. If there isn't, we're going to reset everything to be able to receive the next packets. After processing all the data, if we have less than or equal to 1 byte, we also reset. If any higher, it means that we're still receiving data, so we're going to be waiting. So we're not going to reset right away, we're just going to be waiting for more data to come. So this will still call reset, but this time with false, so it's going to back up by 4 bytes so that it can read the next packet length when it receives more data. So just to show how I add packets to H3MP, since they're hard-coded into enums and the packet handler array, it's going to be a bit different than adding custom ones for mod support, so I'll just show you my process. Whenever I want to send something new through the network, maybe it's a patch I did, maybe I'm following some type of event. So actually, one of the examples I might want to show implementation of is implementing the windows, so breakable windows, breakable glass, and all that. So maybe one of the actions that I want to track is the window breaking. To do this, well, I'd add a patch over probably in action patches or damage patches, and I would then send a packet every time this happens. So what I'll do is I'll start with client send. Here I would add a sending method for that specific type of packet. So we can follow one of the pre-written event here. So we can follow something like C4 detonation. It's pretty simple. It's just whenever a C4 explodes, I send that action over to everybody else so they can explode it on their side as well. So what I'll do in here is I'll make a new packet and I'll instantiate it with the packet ID for C4 detonate. This is really just an integer. I have an enum with a descriptive name, and these are all just packet IDs for different actions. So I'll make a new packet with that packet ID. I'll say the tracked ID of this tracked object. I'll come back to what that actually is later. And the position of the explosion, so that when someone receives it, they can just position the C4 at that position, and then they can detonate it. So when we send this over through TCP, the server will receive this. So we can look for C4 detonate. The server packet handle will always receive the client ID and the packet, so it knows which client it comes from. it'll read the tracked ID of this C4. It'll go and look for the C4 in the objects array if it has a physical counterpart to this C4's data. So if it has the actual C4 object on its own side, the server will get the C4. If this object is actually a C4, it will then set its position and then detonate it. For a lot of these actions, obviously, like when we detonate it on this side, we don't want to send it again. We don't want to send detonation again over to the client. This would create a feedback loop. So if the client sends a detonation order over to us and then we detonate, then the detonation patch says that we've detonated this, so we need to then send the packet over to the client, and then the client does the same thing, and then it just goes back and forth. So we need to prevent the patch from telling us to send this packet. I do this with just a skip marker that I increment in the patch itself. So if this is ever above 0, I just skip it so that we don't send another packet about the detonation. A server will then relay this detonation order to other clients. So this then goes over to server send. We're going to be sending this to other clients. Now, instead of rewriting the data to a new packet, I'm just going to resend the same packet. I have 2 here for this specifically, so if a C4 detonates on the server will just use this, so it will write the data the first time. But if it receives it from someone else and relays it to other clients, instead of rewriting all the data, it's just gonna make sure that the ID is correct and then just resend the same packet. So if the server sends this, it will send it to all clients. Otherwise, it'll send it to all clients except the one that we received the order from originally. This packet will then eventually be received by the client, or another client in this case, and they'll do the same thing. So they'll detonate it on their side if they have the actual physical version of this item instantiated. So when I want to add a new packet, I'll be starting with the client sending this over with a new ID that I'm going to be adding to the enum, and then I'll be heading over to server handle where I'll add a new handle for it, and then I'll be adding it to the list of packet handlers, and then head over to server send, add the new entry to the enum on that side, and then head over to client handle, add the new handler, and add it to the list of packet handlers. This is essentially how H3MP works. So you can see H3MP as really just a tool for networking H3VR data. With it, you can send whatever data you want from a client to another, as long as they're connected to the same server. Using this, H3MP tracks its own stuff. So this is where the TrackedObject system comes in. So obviously the TrackedObject system is used to track objects across the network. Where this all begins is in Game Manager in the sync tracked objects methods. So this is called at specific times. So though, as we've seen before, when we arrive in a scene, we're going to want to track all the objects in the new scene we just joined. This gets the current scene, gets all the root game objects of the scene, goes through all of them recursively. So this will try and find types of objects that we can track in the scene, and then all these tracked objects will be synchronized across the entire network, across the clients. So for every transform related to the root game objects, we're going to be looking at whether the corresponding game object can be tracked. So if it is one of the tracked object types that we've registered at the beginning when we initialized H3MP. To do this, we're going to pass over the transform, and then we're going to go through each entry in the tracked object types. So let's go back to that first. So when we initialize H3MP, we get all the tracked object types. So if you want to implement a new tracked type, as long as you include this type in your assembly, H3MP will find it and will add it to the registered ones. So how it does this is H3MP will get all the assemblies that are currently loaded, it will get all the types from those assemblies, and it will check if this is a tracked type. To be considered a tracked type, the type must be a subclass of tracked object data, it must have an isOfType method. This will be used to check if the game object related to a certain transform is indeed of this type. It must have a makeTracked method, which will be used to actually track the game object corresponding to the given transform. So both of these methods must be static. The isOfType method must have a return type of Boolean, and it must have the first parameter be a transform. The makeTracked method must have a return type that is subclass of TrackedObject, must have first parameter type be transform and a second parameter type be of TrackedObject data. I'll look at actual implementations of these so you can see what I mean. If you have a type that inherits from TrackedObject data, but somehow you don't have one of these, or they don't match any of the requirements, you'll get an error in the console telling you that the specific type is missing the minimum requirements to be a track type. Once this is considered a track type, we're going to be adding it to the track types. I keep track of these in a general dictionary of all the track types. I keep them by name so that I can access them easily later. This is mainly actually to identify them across the network. You'll see why later. So I also keep these in a more specific one. In this dictionary, the types are sorted by who they inherit from, so that I can then track objects properly later on. I'll explain this in more detail later, but essentially this is a dictionary of lists of types. So if there are no other types in there yet, I'll just add the current one to it. The key is the type, and the first element in the list of types is the type as well. If another type must be added to the dictionary that is inheriting from this type, it will be added to the same list. If, on the other hand, it is a superclass of this type, so if this type inherits from the new one, a new entry will be made to replace this one. Essentially, the key and the first element will always be the most generic type of the types in the list. This is because when I track a new object, if, for example, I have an object that can be considered an item, so it has a physical object component on it, and it can be identified in the item manager's object dictionary of the game, but it can also be identified as a subclass of tracked item that maybe a mod has implemented and has inherited from tracked item, then I won't want to track the object as a tracked item. I'll want to track it as the subclass. So I need to sort these types in order so that I can check them in the correct order so that I don't track them as the more generic type. I'll track them as the more specific type. So I'll go through this list in reverse order so that I always track an object with the most specific type corresponding to the type. I'll be going through this whole process later when we actually go through the tracking process itself, and maybe it'll make more sense then. But essentially this is what I do, so I just make sure that everything is sorted properly here so that I can check them in the specific order I need. If the type isn't already found in the dictionary, we just add it because it is a new entry. Now a mod can add its own tracked types. This will happen when H3MP gets loaded. Obviously there might be some assemblies that have not yet been loaded, maybe something gets loaded late because of the load order, so H3MP might be missing some track types. So if your mod implements some track types, you might want to make sure that it is already in the TrackedObject types by name dictionary. If it's not there, you'll want to call add track type with your new type. Just make sure that it is a track type first. So going back to the tracking process, once we know all the tracked object types that a tracked object can possibly be, we're going to be checking on each transform in the scene which type it is. This is where the isOfType method comes in. So for each transform, it's going to go through each track type we have. Again, like I explained earlier, it's going to go through these in reverse order for each entry in the dictionary, so we check the most specific type before. If isOfType returns true, so if the transform is indeed of this track type, we add it to a list of all possible types this can be. this can only be one type in an entry of the dictionary, but it could span multiple entries. So if here I have a tracked sausage by default in H3MP, but what if there is some mod that adds another track type that matches the same requirements as sausage, does not necessarily inherit from tracked sausage, then this will match tracked sausage and the other custom track type that this mod introduces. So to deal with this, if the transform doesn't match track type, obviously return false, and the track type that we return is null because it cannot be a track type. If it's only one, good, we return that type. We return true, we found a type that is matches. If it is multiple though, maybe this type specifies that it overrides certain other types. So this other tracked sausage type that the mod introduces might specify that it is overriding tracked sausage. So to use that one instead of tracked sausage. To specify these, a custom tracked type can implement a getType overrides method, which is expected to return a type array. This type array should contain all the types that this new custom track type is meant to override. I might change this over to a string array just because you might not actually have the actual type, but you might just know the name of it. So I'll be changing this later on, and I'll be instead checking for the names of the other types. But essentially what this will do is, given the overridden types, it will remove any of these types that it finds in the list of possible track types. If there are none left after, it means that types are overriding each other. So we're just going to take the first one in the array that we kept before we eliminated all of them. So this is what we're going to return essentially. We're just going to return the first one we get. If there is only one, perfect. It means the overriding worked, and there's only one left. So this is the one we're going to return. If there are multiple, that means that the possible track types did not override others. Again, we're just going to take the first one we find in the list. In any case, if we found multiple matching track types, we will return a type in the end, so here we return true. Once we found a track type specific to this transform, we're going to check if it was already tracked. If it was already tracked, we're just going to ignore it. We're just going to return. If it did not already have a tracked object on it, we are going to continue. So we're going to check if either we control everything. So this will be true if we are the first in the scene, for example. Then we know that we can control everything, so we're going to track everything. If we do not track everything, we still obviously want to track, for example, items that we are currently holding in our hands or that we have in quick belt slots, for example. This only applies to track types that can be interacted with in any way. So in my case, it's really just tracked item, saucigs, and autometers. We don't count encryptions because you can't hold encryptions. So this will be called on the track type. It will try to call an isControlled static method in the track type. If this is not implemented, fine, it'll be null, it'll return false, and that's it. It's not implemented in encryption, but it is implemented in tracked item and sausig. If it is implemented, it has a return type bool, and the first parameter takes in a transform. We will call it and return that result instead. So if we want to track this object, we will then make this object tracked. This is where the make tracked method comes in. So it will get the method from our type and it will call it with the transform and a parent if applicable. I'll come back to parents later. Just to keep track of tracked objects that are maybe parented to other tracked objects in this scene's hierarchy. So once we have the actual tracked object, we're going to be looking at the make tracked implementation later. Once we have the tracked object, we're then going to want to sync it with other clients. So we're going to check if it is awoken. If it is, we're going to sync it. Otherwise, we're going to keep it for later. So we're going to set a flag telling it that when it does awake, we want to send it. If it is already awoken, if we are the host, we're just going to add it right away to the global tracked objects list. For the client, on the other hand, we're going to need to request the server to add the tracked object for us. So we're going to add it to a temporary local waiting list of objects. And then we're going to send the data of the tracked object over to the server, and the server will process it for us. Once we've decided when and how to send this tracked object, we're going to continue down the hierarchy recursively to go through all the transforms in the scene. So let's go through the tracking process through the network. So when a client wants to add a locally tracked item that doesn't yet have a tracked ID, it is going to set its local waiting index, which will be a unique integer, and it will then add the object to the waiting local objects dictionary, which uses a local waiting index as the key and the data of the object as the value. Then the tracked object data will be sent over to the server. This sends a packet with the tracked ID tracked object, and it will then ask the tracked object to write itself to the packet. In this case, we want to write the entire data of the tracked object on the packet. So we'll set full to true and send everything that another client would need to instantiate the item on their own side. This for different tracked objects means different things. So for a tracked item, for example, we're going to be including an item ID. This is going to be used to identify the item in the item manager's object dictionary, from which you're going to be able to get the prefab and instantiate it. So note that this is a virtual method, so it will be overridden by another track type. So like tracked item, if we go over to write the packet, this will call base, but it then will write its own data. So like I said with the item ID, it's going to add the item ID, any other identifying data you might need, and additional data. Then it will write the data that the track object will need to update itself. This is the data that will be sent every frame to update the tracked object. So going back over to tracked object data, in the case of the generic tracked object, this will be the tracked ID and whether it is active or not. So we're going to write our tracked object to the packet, and then we'll just send this over to the server. When the server receives the tracked object, it is going to call add tracked object with it. Add tracked object will decide the tracked ID for the object. So essentially, a tracked ID is the index of the tracked object data inside the global tracked object list. The global tracked object list, by that I mean this here. So the server has literally an array of tracked object data. The index of a tracked object data inside this array is the object's tracked ID. By default, all tracked object has a tracked ID -1. So when it is sent by a client, it does not yet have a tracked ID. It's going to have a tracked ID -1. So recall how I talked about when multiple clients join a scene at the same time, they might all track their own objects. The server will know exactly which client got there first. So the server is going to decide who gets to track any tracked object that was initially tracked in that scene. So if this is a scene initialization tracked object, but they were not the first in the scene, it's going to return this data to the client that sent it with a tracked ID of -2. This will indicate to the client that they have to destroy this object on their side instead of tracking it. So this is going to just resend the data to the same client that sent it, and then return and ignore this data entirely. If this is a tracked object that we want to track, we're going to make sure that there is space in the objects array. We're going to give it its tracked ID, which is just going to be the next available index in the array. We're going to remove that index from the available indices, and then we're just going to set that position of the array to the tracked object. We're then going to add it to a local tracking dictionary where we track all the objects by scene instance. Once that's done, we're going to check as well if this tracked object has a parent, and if it does, we're going to add it to the children's list of this tracked object. If we can identify this tracked object locally, we might want to instantiate this item right away. So first we're going to check if it is not our object, because if it is our object, it means that we're the one tracking it, so we already have an instantiation of it. We don't need to instantiate it. And then we check if the object is actually identifiable. This calls a virtual method in TrackedObject which I can show you. This is the implementation for a tracked item, so it checks if it can find it in the item manager's object dictionary. So if it can, or if the ID is a teenage chatable crate, which is something specific to this implementation, I'm then going to get true as is identifiable, and then I'm going to check if we're not already waiting for instantiation, if it's in the same scene, and if it's in the same instance. We're going to start the instantiation. Then we're going to want to send this data to all other clients in the same scene instance. So we build a list of all the clients that we want to send this to, and we send it. This here will be handled by the client similarly to the server. So it's going to call an add tracked object on the client class. If this now has a tracked ID of -2, it means that we need to destroy it. It means that it was ours, and the server told us that it's not going to track this, so we need to just destroy it. So we get rid of any reference for it. So we get rid of the waiting local object reference of it. We set the necessary fields, and then we just destroy it. If we don't destroy it, we're going to make sure that the client-side objects array is large enough to actually contain the tracked ID of the tracked object. Once it is, we're going to handle the data differently depending on whether we were the controller or not. So if we are the controller, note that the tracked object that we receive through this is not the one we tracked. It's a copy of it. So the only data that'll be different will be the tracked ID. So essentially we want to get the original tracked object data that we originally stored in waiting local objects at the local waiting index. So if we're able to find this, we're going to get it, and then we're going to check if we were actually the original tracker of this. Once we got the actual tracked object data, we're going to remove it from the waiting local objects dictionary. We're going to set its tracked ID, and then we're going to set it on the local objects array. Like the server, we're also going to add it to the objects by instance by scene dictionary. Now, while a tracked object was waiting for its tracked ID to be received from the server, some things might have happened. So maybe the object was destroyed while it was waiting. So if this happens, the tracked object will be added to the unknown destroyed tracked IDs list in tracked object. There are other actions like these, so that if these happened while we're still waiting for our tracked ID, we're going to add them to these lists or dictionaries so that we can process them once we do receive the tracked ID. So, for example, if the tracked object was destroyed while we're still waiting, when we add it locally, we're going to be calling on tracked ID received. Here, we're going to process all the entries of these lists and dictionaries. Here, the example is the unknown destroyed tracked IDs. If this tracked object was an entry inside this list, we're going to send an order to everybody else to destroy this item as well, and then we're going to set this to null on our side, remove it from the list, and then remove it from local. So we're just going to get rid of it completely, but we need to make sure that we tell everybody else to do it, because now everybody else has the object, but it was destroyed. So going back to the adding tracked object, we are then not waiting for this anymore, so we just set this boolean to false. If this was false, so if we were not actually waiting for this tracked object data, it means that this tracked object data is the first one that we got, so it's not some copy. So if we were not waiting for this tracked object data, we're going to check if we already have one at this tracked ID. If we don't, we're going to add it, the same thing we do above. Note though that additionally to adding it to the usual tracking lists, we're also going to add it to the locally controlled tracked objects, because this all happens in the case that we are the controller, but somehow did not yet have the data for the object. If we were not waiting for it, it means that we might not yet have the physical object. So in that case, if possible, we'll want to instantiate it. If we were not the controller of this data, we check if we already have the data for it. If we do, we might want to instantiate it, so we go through that whole process and then we return right away because we already have the data. If we did not yet have the data, we're going to add it to the list like we usually do, process the parent, and then try instantiating it. So this covers the two cases of whether a server adds a tracked object or a client sends an object to be tracked. Once this is done, an object will be considered tracked. So when this is done, we might want to do something right away when we track this object. So this is why I have an onTracked method on the tracked object data, which can be overridden. Tracked item data overrides this. Tracked item data overrides onTracked to handle the case in which a SOSIG might have picked up the item before it was tracked. If the SOSIG picks up an item that is not yet tracked, it's going to add it to a dictionary that we're then going to check to see if it contains the item we just tracked. And if it did, then we're going to handle the case accordingly. Now, when a tracked object was not awoken yet, and we need to wait for it to awake before we actually track it, if it awakes eventually, tracked object awake will make sure that its data is up to date, and then will do the same process. So if it's a server, it's going to track it right away. If it's a client, it's going to send it to be tracked. In the case that we do not control everything and we do not control this specific tracked object, we're going to want to just destroy it because it's an object that's going to be tracked, or that has to be tracked, but it's going to be tracked by someone else, like someone who was in the scene before us, for example. So below, if the transform cannot possibly be tracked, I'm just going to keep going down the hierarchy recursively until we've gone through the entire scene's transforms. So I'll end this first part here. In the next video, I'll talk about the current track types I have implemented, then go through customization with custom packets, then customization with custom tracked objects, and finally implement a tracked object from scratch to be used as an example to add new ones through mods.